delay. This is the first American session on 3DGB this year. So happy New Year to everyone. Also happy new president today. Our good timing. So today we have another exciting program. We have Hao Su from UCSD giving a talk, and joined by Shubham Tulsiani, the Facebook AI Research Fair, and Chi-Xin Huang from UT Austin for panelists. I didn't really have to introduce Hao, but let me just briefly give you some background. So Hao Su is an assistant professor at UC San Diego, Department of Computer Science and Engineering. He got his PhD from Stanford under the supervision of Leo Guibas, the Center of Geometry Processing Research. So we are excited to have Hao Su today. Hao, so please take it away.
Oh, thank you very much for the introduction. Okay, so hello everyone. I'm so happy to meet you here. Actually, meet you here. Okay, so the topic that I'm presenting today is compositional generalizability in geometry and policy learning. Okay, so in the past decade, we have seen that deep learning has swept the field, right? And there are a lot of successes of this tool. For example, in image classification, speech understanding, and also in our interest of 3D shape recognition. So there's a commonality behind these successes. There's a common framework that usually we have prepared a big data set for each task to work on. And also there's like a learner, which is a function that takes the image or 3D data or some kind of other data like text as input. And this learner has parameters and predict labels. And also for the learning of the model, there's a referee, which is a loss function. So we minimize on the training set the loss. And in this track, deep learning, especially like convolutional neural nets or multi-layer perception, this kind of large and deep neural networks has taken the lead. Okay, that is because the universality theorem says that, well, for any function, it could be realized by such kind of like a deep neural network. And this is something that we all know. And success is actually at the cost of using a lot of data and a lot of computing power. So basically, we have to curate the data sets for every task, assuming that, well, a train and test data sets are the IID samples. And if the data set is large enough, we would expect certain kind of a so-called generalizability. Okay. However, they emphasized, or the focus of the day is that we feel that, well, having like large-scale training set aligned with the test set is often insufficient to deal with the real-world complexity, because the real world has combinatorial complexity. But what we were taught and practiced in school may not be what we have to achieve when we are like in our work. Okay, so in contrast to like the standard setup I just mentioned, which has been successful, compositional generalizability provides a natural curriculum. It's like the training is done on a small set of problems to learn the basic skills and some knowledge of how to compose them. But the test would be to solve a more diverse set of tasks, and probably by recomposing the basic skills and also through certain kind of exploration of a novel task. And this is more aligned with how people learn and apply knowledge. Like think about how we learn about Newton's law from high school to like to university. But like for some of those people, engineers, civil engineers, they will use them to build very complex structures like buildings. And this kind of perspective actually has history in artificial intelligence, like the graphical models. They take the compositional generalizability view. Especially in this talk, I will present some of the latest progress in my group, which is about like the compositional generalizability in embodied AI. Okay, so somehow embodied AI is a type of artificial intelligence with a body and with the purpose of interacting with the physical world surrounding us, surrounding the agent. And we will focus on two questions. Now, one is about like the geometry aspect, and the other is about the interaction aspect. Okay, so for the geometry aspect is about, can we guess the 3D structure of unknown objects in the environment? We assume that the agent is interacting with the environment, and there will always be something that are not familiar with. Like even for us humans, well, we have been educated much. This still happens. Think about when we are browsing the Amazon website, right? There are always the interesting products. Somehow we can guess their structures out of like a single photo or just a small number of photos. And the second question that we ask is, how can we generalize the interaction scales with the environment across tasks? Okay, so I will first introduce our work of zero-shot single image to 3D structure prediction. So first, let me be clear about the task. The task is, we have a single image from a category.
Hi, I lost Hao's audio. Shubham,
Hello?
you get the audio from Hao?
Yeah, I'm still getting the audio from Hao.
Oh, sorry, just my issue. Sorry, please go ahead.
Okay, maybe I'll just proceed then. Okay. Okay, so the setup is you have a single image of a certain object, and you want to like give an image predict the 3D. And also we assume that for the training set is one category or a few categories of objects, whereas the test time is a very different category. It's a set image from an object of a very different category. Like here, we train on chairs, but we test on beds. So this single image 3D reconstruction problem has been hot in the past few years in vision and graphics communities, but most of the work has explored the like low-level representation as like a voxel or a point cloud or a surface mesh representation. And the setup is in the training and test data are from the same category. And there has been a number of studies that tell us for those approaches, if they are in a cross-category setup, they could not give us satisfactory results. Starting about 2 years, more than 2 years ago, there start to like be a group of researchers who are more interested in the problem of 3D prediction from single image for novel categories. And this is a representative pioneer work. And the idea is, given a single input image, I first predict a per pixel depth map and some other 2.5D information. And then from this information predict from single view, do a shape completion by hallucinating the invisible part. This is driven by David Ma's theory. While this approach seems to have better performance compared with those like just designed for the same category setup, practically there are still issues. For example, here is the model trained. Here is a neural network trained from like chairs and tables, and I forget, maybe airplane. Yeah, maybe it's chair, table, airplane. But somehow the test image is from the training set. The test image is a shelf. Now we can see that the prediction, well, still has the global shape similar to the training data, like the chair. Okay, so this is not so, not so satisfactory to us. So there are many possible reasons. One of the possible reasons is like depth prediction itself is not really a simple task. Like we all know, depth and shape has difference, right? And shape is more like for the relative properties, whereas the depth is more for like the absolute position. So for the two images, it's very similar depth, very similar image appearance. They could have very different depth. And besides, usually people will assume that they are predicting depth in the canonical space. However, for objects from noble category, the canonical space itself is even ill-posed the problem. Okay, for the prediction. And there might be other issues, like usually this work use the fully convolutional structure and do per pointwise depth prediction. And it's hard to control the receptive field. So the global, so usually global shape prior is like a, deeply rooted in the decoders. So that's what you see. The decoded objects is always like with a global shape like the training data set. And here we explore a different route, which is the more modularized approach as a starting point of verifying the idea of compositional generalizability. And we use part as the composable units. Okay, so then for our setup is we learn to lift an input image from a single view to like an assembly of parts. Especially in this work, we are assuming that the parts are as simple as the cuboids. And we hope that this cuboid assembly job could have done a better generalizability for those in the, for images in the test set, which are from the novel categories. So, using parts as the primitives to compose shapes is a long history, actually. The idea dates to like decades ago in the study of computer vision. And we're kind of revisiting this classical idea. Another motivation that drives us to consider part as the starting point of understanding for the new shapes is because part has a special role in the embodied AI context, in my understanding. Because when people talk about like interaction with the environment, you are interacting with objects, and the interaction with objects is actually done through the interaction with paths. So paths are the handles for interactions, and understanding the paths help us to predict how to interact with objects. So for my group, we have been pushing the direction of path-based shape understanding for years. Especially in 2019, we have built a large-scale part-based database. Okay, for example, for 26,000 3D models, we have over 500K part instances. And somehow in the process of annotation, we are also aware that although this category set, like 24 object category, doesn't seem to be so large, the part actually already, when it is decomposed at the part level, the similarity across categories is actually quite large. In other words, like different categories share a lot of common parts. So that brings us like the interest of testing whether it's possible for us to use the parts from just a single category and like try and being able to predict a structure for other categories that are very different. So in this work, I'm introducing a zero-shot structure prediction that is trained using just the chair category. Okay, so for our training data, we use the PartNet chair models and render them into images. You see that they actually have the texture and highly varying pose. And we also use the path annotations. So this is kind of a supervised work, not the type of a very fancy unsupervised or self-supervised work that you have been seeing a lot in the past year or even in the past month. Okay, but we think that this could be a very good starting point and a strong baseline, and helps the community to make progress. And the test categories are 3 different categories, like a bed, cabinet, and table. So let me first, I'm sorry. So let me first give you an overview of the whole pipeline, which is actually straightforward. So given the input image from a single view, we first do a part detection on a 2D image space. We hope that this part detection would transfer across categories. And once we have the part mask from a single image, we start to predict the geometries of every part. It's like including the rotation and the size. And lastly, we will predict the relative position of the parts and try to assemble them to be a 3D reconstruction. So the high-level pipeline is straightforward, okay, as anyone might imagine. But the true interest in us is not in the high-level pipeline. The point is, okay, so we treat it as a decomposition of the high-level problem to sub-problems. And can the sub-problems be solved with cross-category generalizability? That is the point. Is this the proper decomposition of the problem so that the solution could be generalizable across categories? Okay, so let's inspect and give a rough inspection of the sub-problems one by one. Okay, the first question is the transferability of image-based part segmentation. Okay, this is instance level segmentation work, and we use the mask RCN. The mask RCN actually is a 2-stage framework. Given an input image, it first generates a rough bounding box of the parts, and then it will use this bounding box to crop the feature map, and then do subsequent processings to predict the precise per pixel instance mask. And we find that this part proposal bounding box is very important step. It helps to isolate the region of interest, the part instance, from the rest area of the image. And this isolation is very helpful for the cross-category generalization. And there's a result that we have trained the mask RCN just using, in a supervised manner, just using the part from the chair category. And we evaluate it on 2 novel categories, which are the table and the bed. And we put some representative examples here, and you can see that the result is actually pretty decent. Okay, now you can see, especially for the bed category, by our annotation, this region is a part, and in our prediction, it's a part, right? So you can see for other kind of bar structures, the prediction are quite reasonable. Okay, so we see that actually 2D based the part prediction gives us good performance, although there's space to be further improved. Okay, the second step is to predict the part attributes. So given the image and the mask of a part, we want to predict the properties of the parameterized 3D bounding boxes of each part by their rotation, size, and the relative position of the cuboids. And we will use the parts relationship to help the prediction. And we will give you more details later. Okay, so let's take a look at the prediction of the rotation. The input, so basically, we will build individual deep neural networks for each sub-problem. And for example, for the part rotation prediction, the input is the image and the part mask, and the predicted label is the rotation of the part. And there are 13 key tricks that makes the approach really work well. and we will explain it later. But let me just give you the visualization of the result. Okay, so here we train the per pod rotation prediction on the chair data set, and we will evaluate on not only chair, but also table, bed, and cabinet. So here we're just assembling the parts of objects in ANOVA categories using the ground truth rotation and relative position. So only the orientation is predicted. But you can see that the orientation of parts is really well predicted. Okay, so for this part, this is really a transferable module, which to us is important. Okay, this kind of observation is important. Okay, so sorry. So you can see that this is the input image of the table. I'll just test the data. So for this example, I would say that it's an example that's very different from the chair categories. And like for the beds, the bunkers, they also have a very different geometry from our training chairs. However, the orientation of parts can be well predicted. Not only for those that are like horizontal or vertical, when there are certain slanted structures, they could also be well predicted. Okay, so the rotation prediction may be achieved with high quality. And the second part is the size prediction module. Okay, so we have predicted the orientation of the bounding box of each part. And then for each part, we try to predict the dimension of each axis of the orientation. So here we think that like for the orientation of a part, it could be like represented as 3 vectors. The 3 vectors represent the orientation, and we compare each of the vector with the input image as mask to predict like the dimension of it, of it. Okay, so there are also certain tricks that makes this part work, and we will explain the details later. And let me just, before explaining the techniques, let me just give you like some visualization of how well can the lens prediction be. So this is the same group of images as the rotation prediction. And we here use the predicted lens, but for other properties like the orientation and path relative position, we use the ground truth. And we just want to verify like whether the length of the or the size of the bounding box can be well predicted. And you can see that the quality is again quite high. Okay, this is possible to be trained with very strong transferability. And the last part is we will assemble the parts to be a whole chair. Okay, so this assembly is based upon the part adjacency relationship. So we will guess the adjacency of parts based upon the input image and the part masks. And then based upon the adjacency prediction, compose the parts. Okay, so there are 2 steps. The first step is, given the input image and the 2 part masks, we use independent neural network to do a classification job of whether 2 parts are adjacent to each other. And you can see from the performance table below that the adjacency classification module with our way of setting up the input could be quite transferable. Like the performance on the chair dataset, which is the training dataset, and the ANOVA categories are not very different. Okay, so once we know the adjacency between parts, we can start to predict their relative position of the centers. Okay, and this relative center position, there are certain tricks that I'm not going to explain in detail, but with the tricks, it's possible to predict quite well. Okay, so the input is the image two-part masks, and the prediction is a vector that's pointing from the center of one part to the other part. And here we have diagonalized the object. We have normalized the object with one meter, diagonal bounding cuboid of the whole object. And you can see that the error for the relative position in this unit cuboid is pretty low. Okay, so if we visualize the effects, you can see that the relative position prediction can well assemble the parts together. And note that for our approach, in fact, the orthogonal angles between like the seat and the legs, this is able to be properly predicted. And we think that, especially since we are working on the man-made objects, there's very strong regularity between the relationships of parts. So that makes the transferability relatively easy. Okay. So when we decompose the problem of single image to 3D into parts, we get to boil it down to the small problems, and each of the small problem is much easier with us. Although the training data and the test data are very different, but when we are decomposing the problem into the parts and the parts relationship level, the similarity is very high, and that increases the chance of transferability. Okay, so although we have been emphasizing that for this talk, it's in a setup when the test data and the training data are from two different distributions. By factorizing the problem into modules, although the joint probability are very different, the factorized version, okay, the individual components, they have much better distribution alignment. Therefore, the transferability is much better. Okay, so I'm going to explain some of the key techniques that improves the performance of our system. In fact, there are certain key tricks that are invented when we were building this pipeline. So without these tricks, the performance will be much worse. Okay. So first of all, we have to tackle the ambiguity caused by the symmetry of the 3D bounding box representation of parts. Okay, so many parts are visually and geometrically symmetric, like chair legs. And as illustrated in the top right figure, if we predict the rotation of the chair leg with 180-degree rotation along the symmetry axis, the prediction should not be penalized. And another important issue for us to address the ambiguity in orientation prediction is that for the ground truth bounding box of the parts, they are obtained through doing a principal component analysis to the part point clouds. And we all know that for the PCA, okay, so the principal components are ambiguous up to the direction. Okay, so chances are like subparts with the same appearance may have very different rotations, as illustrated in the bottom. Okay. Okay, like for the left and the right legs, they are actually parallel paths. But if you do the PCA may just flip the two small principal components. Okay, the orientations is very different. So we have to address this kind of ambiguity in the training label. Okay, and also to some of the noises in the training data, which seems like inevitable. Okay, so in order to deal with the issue, we use a proxy loss, which computes the earth mover distance between the corners of two unit cube. representing the orientation of the ground truth rotation and predict rotation. And we find that the Earth mover distance in the setup is much easier to optimize than the widely used chamfer distance, given its 3D bounding box case. And furthermore, in order to deal with like the ambiguity in the ground truth, we actually have to train with the mean of n loss to solve the symmetry ambiguity. And concretely, we will select the minimum loss among all the predicted rotations that are symmetrically equivalent. So that helps us to break the local minimums. A second part is when we're trying to predict the rotation, the rotation parameterization actually has a lot of challenges. When you are using them in the neural network, it will cause local minimums. And this is, the consequence that there are topological differences between the spectral orthogonal group and the Euclidean space that we use to parameterize the rotations. So dealing with the singularity of the rotation parameterization in network training is really a tricky issue. And the issue has been brought up in the community. Somehow we have been like exploring how to address it. Okay, because this is a kind of a local minimums caused by the topological difference. And we finally realized that a kind of very helpful practice to overcome the challenge is to design multiple branches for the prediction rotation. And we also choose to use quaternion as the representation of rotation because it has a number of properties that makes it suitable to be used in neural networks. Okay, so however, since so because of topological difference, the quaternion representation of rotation is actually not unique. So we actually use multiple branches to predict the multiple quaternions. And then this could prevent a network spending most efforts fitting a discontinuous function caused by the topological issue. And we actually model it as a mixture of atpers. So different branches output both the quaternions and the probabilities to choose a corresponding quaternion. And the objective is to maximize the log likelihood given the predicted quaternion and probabilities. And this, this is quite effective as verified by experiments. So the last row is the baseline approach that if you just follow like the common practice in a community for quaternion regression and for the proxy plane, we should approach that, that has taken the symmetry and the mean of n loss into consideration. Now, if you further use the mixture of aspert formulation, we can get a much better performance. Okay. So again, the training is armchair, but the evaluation are on novel categories. And we can see that with the proper implementation, the prediction is actually really generalizable. Okay, so the key technique 3 is the group-based size prediction. Okay, so we will predict the size for the translational symmetric paths in a group. So we will first use a classifier to detect the part in the image that are translational symmetric. Okay, and then we'll try to predict the size of the paths in a group altogether. It's like we build this kind of input, given an image and a path, we process it by ConvNet. So for other paths in the group, we will process by the ConvNet sharing the weights. Okay, so then finally we will predict the size of the path for the whole group. Okay, to predict the size of the path shared by the whole group. Okay, so this actually is a very helpful practice, especially for the case that you have multiple parallel pods. If you predict their size individually, this is the result that you see. They do not have the same size along different, like along all the dimensions, although obviously for us humans, they are the same size. And worse still, because we will use the orientational size as the prerequisite for the next step of predicting the relative position of the pods, you see that the relative position of the pods are also affected. Whereas if we predict the size of pods at a group level, we could guarantee that, like in a group, the pod size are much better predicted. This should be relevant to the fact that by taking the group of pods altogether, we're able to fully leverage like the perspective transformation. Okay, so or to like to get the information to handle the perspective transformation. Predicting each part individually, you're not able to handle this point well. Whereas as a group, it helps us to solve the perspective effect. So we can see that the measured by one distance, the group-based size prediction gives a much better, it's not much, relatively better performance compared with like predicting the sizes individually. Okay, and there's actually another effective trick that has been used repeatedly in the whole pipeline, which is we provide the pod mask as the input. And this is kind of a explicit attention map. And the neural network learns to isolate information irrelevant. It seems like we didn't give other kind of a strong regularizers, just this past mask is really useful. Okay, so let me now show you more results. First, the models are all on chair. Let's test it on chair. So for the result on this corner, this is using a graph neural network. Okay, now we see that when the training and the test categories are from the same category, like train from chair and test on chair, all methods, including ours and the graph neural network based. And sorry, I guess the video is a bit fast. And the genre, the depth map based approach could all work reasonably well. But when it comes to novel category, we will see that for this pod-based approach, it gives much more reasonable results. Now note that this result is not as beautiful as we show for each of the components because there's kind of a accumulation of error, okay, for the whole system. And we obviously see that before the bad category, I'll just pause a bit. You see that from the view that is this is like a bit symmetric, but a space copying effect, genre is able to like predict something a little bit like a bad. Okay, and for the graph neural network and another image-based pod-based approach, it's actually still trying to, which is like a holistic approach and a big network. Okay, so the prediction, it seems like it's still biasing towards like some chair-like thing. Now, if you're looking at the prediction from like novel points, for our prediction compared with the ground truth, you can imagine that the structure is still reasonably correct. Whereas for the baseline approaches, it is even more challenging for them to work well. And here's an example for the bed. Our results is also not perfect, but somehow the structure, it does look like yeah. So for this bookshelf example, we can see that our result is even better. I want to emphasize that we are not the only work that considered to use pods. However, I'd say that the community is pretty aggressive. Like when people think about using pods for the shape level reconstruction, people kind of believe that graph neural network is the de facto tool. And It seems like the first work for pod-based single image 3D reconstruction is from using graph neural network. However, the end-to-end learning of graph neural network doesn't seem to be the correct practice if you are taking the cross-category generalizability in mind. There has to be something done properly for graph neural networks to transfer. And we will talk about that later. Okay, so the conclusion is, while neural network saves us some efforts from feature and predictor design, for compositional generalizability, identifying the reusable modules and their interfaces is very important. And end-to-end should be like define right form of modules for downstream tasks. I'm sorry, I think I forget to play. Okay, instead of being interpreted as just using gradient descent to optimize the whole framework. Okay, so I will be a bit fast in explaining the second work, which is the compositional policy learning, and also how to achieve compositional generalizability by graph neural networks. Okay, so policy is about the interaction scales. When agent observes an environment and interact with it. And the policy in a community is often represented as a symbol pi, which takes the environment state S as input and action A as the output. And policy learning has been hot in recent years, and the leading methods are reinforcement learning and imitation learning, right? So in the recent literature, in this work, a policy pi is often represented as a neural network. And for the state representation, people there's a trend that people like to use the visual input. Okay, so policy learning is important, of course, important for embodied AI, but what is the compositionally generalizable policy? To illustrate the idea, we actually use a simple game as an example. So for this Pac-Man game, when you are trying to learn to play the game, okay, you might learn in the environment with few dots as foods. And then when you master the scale of eating the dots, you will try to test in a more sophisticated environment. And suppose that we are trying to learn about the policy in the imitation learning setup, that we have a lot of demonstrations, which are the image and action pairs. How do you learn a neural network that is trained from a small scale or simple environment, but would work well in a test environment? Okay, and obviously, a proper level of the modeling of the environment is important. We need to find a proper input representation as how we represent the objects in the environments. And also, there has to be a reasonable reasoning mechanism attached to it. Okay, like once you have certain kind of structured representation of the environment, or in the latent space, it gets structured, you probably could choose the popular choices of a graph neural networks or transformer. And that might be like some of the popular options. And in our work, we thought about experimented to use the graph neural network to build the policy network. Okay, this is because it's kind of more affordable, and we think that it's a simpler starting point for us to understand the generalizability for the policies. Okay, so a natural practice is, now you will first build an object-centric graph, a scene graph from the observation. And probably you will treat each of the object as a node of the graph neural network, and the edges as pairs of or like a more higher order of object groups, and train the GNN. So the question is, can we just expect that a graph neural network learned in such kind of setup will generalize? We did observe a number of papers make this kind of a claim. However, we feel that there might be certain tricky things. Okay, so here we did a sanity check first on some graph theory problems. Okay, so basically we are going to use graph neural networks as the policy, and part of it is reason over the scene. Okay, so it must be able to solve certain kinds of problems like shortest path if you are doing navigation or grasping. Okay, so why don't we just do the sanity check on this kind of graph theory problems, which has a pure form? So the setup is we're going to train to solve some graph theory problems on small scale graphs and try to evaluate its performance on large scale graphs. If the graph neural network works, well, problem solved. If it doesn't, maybe we should think about some innovation to improve the networks. So let's first see the sanity check. Now we try to solve the shortest path. On some of the random graphs, like planar graph or those raining graph or king nearest neighbor graph, lobster graph. Okay, and we use the random graph generation algorithms to generate small scale graphs for training of graph neural networks, like 30 nodes. And then we will just evaluate this model, this GNN on larger ones, like 100 nodes. And we evaluate the performance. Somehow the 38, 39 are two representative graph neural networks in the community. However, you see that the relative error, here's the metric, is not so good. Okay, 0 would be the best. And if we evaluate the connected component counting problem, the counting accuracy would be like 100% to be the best. Using a similar setup, train on small scale graph, but test on large scale graph. The performance is also not satisfactory. We even tried a harder problem, which is like the travel salesman problem, right? It's an NP-hard problem. And still use the relative error as the metric, 0 to be the best. Not surprisingly, for the 2D TSP problem, the graph neural network doesn't seem to be like well generalizable. Okay, so in order to improve the possibility of using GNN as a policy network, we need to improve its ability to generalize across scales. And we did certain investigation and surgery to the classical GNNs. So there are two practices that I'm going to introduce. The first limitation of a classical GNN is that we observe usually they have a fixed number of layers. And we do know that in a graph neural network, information propagates after every layer. So after like passing through one layer in a typical GNN, information will propagate to one hop neighborhood. And after passing 2 layers, information propagates to like 2 hop neighborhood. So if you have just a fixed number of layers for the GNN, the information could just be propagated to like finite distance away. Okay. Now suppose that you are working on a large scale graph problem, like the shortest path. The information propagation diameter should be relative to the graph diameter. And obviously that's a problem. Okay, so in fact, if you want the GNNs to be able to solve the graph theory problems with generalizability, then it has to have certain kind of algorithmic alignment with these graph algorithms. And we all know that for many graph algorithms, their complexity is like it's dependent on the problem scale, input problem scale. Like usually you see a while loop, right? While certain conditions not satisfied, you will just run the loop body until the condition is satisfied. And so here, we think that a layer of the GNN could correspond to the loop body, but obviously there's one thing that we need to learn as well, which is the stopping criteria. Okay, so we plug a function to learn the stopping criteria. And in this way, we built a graph neural network, not only with like the layers for iteration body, but also a network that checks whether you should stop. And interestingly, it's possible to like learn the stopping criteria function in an end-to-end manner together with loop body. So by gradient descent. So gradient descent learns to terminate the iteration of the GNN based upon inspection of the hidden representations. And the second trick that we thought about is about like related with number encoding issue in the graph neural network. Okay, so let me introduce the issue. Okay, so intuitively, imagine that we're trying to like solve the shortest path problem on the graphs with like 10,000 or 10 or like 10,000 nodes of graphs. Okay, and you realize that in order to solve the shortest path problem, for the internal neural embedding of the information, it has to be relevant to to encoding like the distance you have traveled from the source point. Okay, and for the training setup, when the graphs are very small and the test graphs, when the graph is very large, the range for this internal encoding is very different. Okay, and out of range numbers would occur in the hidden repetitions. Okay, so the functions that you learned to process with the encoding would be impossible to generalize across scale. And we need certain kind of a surgery to improve the problem. Unfortunately, we find that many graph theory problems are actually positive homogeneous. Like think about the shortest path problem. If you scale the weights of the graph by lambda, then the shortest path length would just scale by lambda. This is actually relevant to the fact that many graph theory problems has a linear programming solution. Okay, so it has this kind of positive homogeneity. And in order to modify a graph neural network to have this kind of positive homogeneity, it's not really difficult. You just need to do two very simple things. One is to remove the bias term in all the layers of the MLP, and the other is to use the ReLU as the activation function. Now, because now the linear layer is positive homogeneous, the ReLU is positive homogeneous, the whole network becomes homogeneous. Okay, so that allows us to handle like large numbers by pushing them to the to the known range when you are training the network. Okay, that would combining the trick of learning a stopping criteria and dealing with the positive homogeneity, the graph neural network could have much better generalizabilities in terms of scale. Like for the shortest path problem, again, we ran experiments using our improved graph neural network. It's able to handle the shortest path on the different kinds of random graphs much better. And for the counting of connected components, the improvement is even more significant. Like this is the counting accuracy, and 100% is the best. And even for the NP hard problem of travel salesman, for doing this, like the two tricks would improve the performance quite much. Okay. So so after sanity check, we kind of know certain tricks to improve networks for a better graph scale generalizability. So now we try to adopt them in the setup of policy learning. Okay, we conduct experiment, which is an environment that we created similar to the Russian terrorist experiment, that we control the falling digit. A digit is falling from the top to the bottom to hit the number that's closest to it in terms of the value. Of course, the input is the image. You do not know where are the numbers and what is how to interpret the picture, the patch into a value. So through the interaction in the environment, you need to learn them. And we somehow have certain kind of self-supervised mechanism to identify objects and plug it with the policy that is built by graph neural networks. And we find that not only can we achieve the game in larger scale, like when we train in a 3-digit environment, it's possible for the model to generalize in an environment that's more sophisticated, test with 9 digits on the bottom. But the possibility for this to happen is actually the task of hitting the number closest to the falling one. Like you have your key to control left or right. So I forgot to mention that. There's the constant velocity falling down, but you use the key to control moving left or right. And the object attributes has to emerge. It's like after playing the game, we realized that for some layers of a neural network, is hidden representation, has visualization that just gives the value of all these numbers. Okay, the method could even work when there's very complex background. So in this way, we're kind of not achieve our original goal of achieving scale generalizability for policies, but also the task has urged certain object attributes to emerge in the process, in the interaction process. Okay, so we observed that there are two recent published works very relevant to our work. One is the NeurIF 2020 paper, which also diagnosed the effect of learning to stop in a graph neural network. The other is a recent iClear paper, which also pointed out that the number encoding issue is preventing the graph neural network to extrapolate. In other words, it's extrapolate. And somehow in our words, we put it in the context of compositional generalizability. Okay, so I want to actually make a note here. While the iter-GN is able to generalize for some graph theory problems and policy learning tasks, we do not think that is already like a universal graph theory problem solver. For example, by our experiment, we find that even though we provide the algorithmic alignment with cross-call algorithm for solving the minimal spanning tree problem, iter-GN is not really able to solve the problem well. I guess even for the more powerful, maybe transformer, treating them as a more universal reasoning mechanism, there are still many very difficult optimization challenges there. Okay, so here I can give a summary that the lessons we learned is algorithmic alignment may be helpful for GNNs to discover modules and generalize. And number encoding issue needs to be addressed. And there are actually many more unknowns to be explored. And I'm going to use like two minutes or so to talk about certain plan. So our motivation is actually to address, the embodied AI problem, but somehow we realized there are so many challenges that so far for the works that I presented, they are kind of like game environment. Okay, but our final goal is actually to extend the set of works to the more realistic setup, which is like to solve realistic problems. And my group is pushing the SAPIEN, which is an interactive environment, so that it allows us to build a rich set of tasks in this kind of virtual environment. And the SAPIEN is not possible if we are not able to curate a large-scale pod-based database that is interactable. Okay, so recently we're thinking to push the direction of doing a rearrangement kind of challenges. For example, in the OCR-TOC challenge, which is a challenge that was held last year in conjunction with IROS 2020, the task is given like a number of objects randomly distributed on a tabletop. How can you organize it into like a planned state? Okay, so but this line of work is still ongoing. And finally, I'd like to acknowledge the leading authors of the work that I just presented, who are my PhD students or postdoc students or visiting master students, and also the sponsors for my research. Thank you very much. And that is for my talk.
Thank you very much, Paul, for a great talk. For the audience, if you have any questions to the speaker, panelists about the talk or any matter, please use the YouTube chat box at the bottom of your screen. Type in your question. So first, let me maybe Shubham, do you have any questions or discussion to start?
Yeah, thanks. Thanks, Hao, for the great talk. Maybe I'll start with one specific question and then more vague ones after that. So
sure.
In the first paper you were discussing, there were these groups for which the size, the size was constrained to be the same across different parts. I was curious on how the group is predicted or known. And for instance, maybe a chair has two front legs and slanted back legs, and the back legs will then be of a different size compared to front legs. And how are these things maybe handled?
Okay. Yeah. So for this work, I our purpose is to discover a pipeline that really works. Okay, so somehow for a lot of the aspects, they are like found through extensive experiments, but not kind of philosophy or design ahead. So this part is really something that we found by experiment. So somehow I think that in the real implementation, there should be, we are trying to compare the length or the dimensions of the path with a certain threshold as the tolerance. Yeah.
I see. Okay. Okay. Yeah. No, that makes sense. Thanks. And yeah, I guess maybe one slightly more open-ended question is, so at a high level, one insight sort of common across both these works was that, if we do have some compositional structure to the task,
right,
and then we can really like leverage that, and that will help us generalize when maybe the structure is preserved, but the scale maybe changes or distribution changes in some way.
Right.
Though in both of the examples you covered, we did know the compositional structure during training in some sense, that for objects, we know that maybe cuboids are a good representation, and we even have the annotations of those. For the second work you were discussing, we knew that there are these images of digits, which are the objects that are there in the scene, and we should really reason in terms of these. So my question is maybe, in more complex real-world settings, do you think it's possible to always know what are these good atoms in terms of which we might reason? And
yeah, that's a great question. Really great question. So here are my thoughts, right? They're not really, I mean, or kind of conjectures. So first of all, I feel that there are two things that should help each other. One is concept. The other is relationship. It's like you have a group of concepts, you combine them and verify them by different relationships. If you find the right relationships, some meaningful predictions or some meaningful consequences might happen. On the other hand, you might also have like relationship as the prior. Okay, so if the relationship there, it's kind of like the rules. You try to plug the concept in the rules, and if like the plug-in is smooth, okay, the concept gets verified. So I feel that's kind of what the two works have illustrated. For the first work, we kind of are aware of the concepts, which are the paths, and we try to find like the correct way to compose them, search for the composition space. And for the second work, what we are assuming is actually, I mean, I've been emphasizing like the algorithmic alignment. Okay, so here, first of all, I feel that it's better for the algorithm alignment to be certain kind of like a weak prior of rules, weak prior of rules, like weak in general. But this kind of weak in general reasoning rules is still quite helpful for the learning, for the gradient descent, to discover the concepts. Actually, I want to emphasize a little bit that here, I feel this experiment is especially interesting. The processes were first run certain kind of object proposals to like, or say, actually we call it like self-supervised object proposals to generate a number of patch proposals. We do not know, like in a region, this is a digit. The input is really just an image, a whole image. Input the whole image, and we generate a number of proposals using like a VE type of stuff. And there are many wrong proposals. There are some proposals that are correct. But we plug it into the GNN reasoning framework, and somehow after a long time of compatibility test between the concept and the reasoning rule, the bad proposals goes away, and the true concept emerges. So I think that, I mean, it's like, yeah, how humans do things as well. It's like, okay, you have a candidates, you have a big pool transferred from other places, or somehow you have some very vague cue, but the interaction process, a downstream task, yeah, consolidate them and select a small pool. It's kind of like the thought process, yeah.
I guess to maybe paraphrase, you're saying that maybe at least right now we need some priors maybe on concepts and or rules, but it's feasible to refine these as we go along.
Yeah, somehow I feel that is universally true for even for humans, right? We kind of causalities are our prior, right? Yeah, we kind of believe like the most basic of logic, and this kind of logic allows us to do discoveries.
Thanks. And actually, maybe one more question, which is maybe not related to the techniques, but the setup. So in the first paper, I really like the setup that you were proposing to study, that is, given one category, you want to learn something that generalizes to other categories. And
exactly.
And as you know, there have been so many different formulations for what setup we should study in the 3D prediction task, like intra-category, or you have 50 categories and you want to generalize to 51st category, or in this case, given one category to many more. And we've also seen many such examples in image recognition where different people have been studying different setups. So I guess the question is, let's say if you wanted to suggest to some student who is starting out, what are interesting generalization setups to study or important generalization setups that we should look at in 3D reconstruction, what would your answer be? Because maybe hoping that we generalize to all categories from a single category, I feel is still not very easy for diverse categories.
Yeah, well, that is another great question. So I feel sometimes when we are designing the benchmarks, we already have kind of expectation of where the richest direction should be. Like for me here, I'm interested in using parts as the basis for transferability. So I would say that when you are making this, when you are having this kind of expectation, there's an upper bound for how much you can do. So when we are trying to push this experiment, we actually did draw the statistics of part and part relationship distribution across categories. And somehow we see that like the training and the test categories, they are very different geometrically, but in terms of like a part and part relationships, yes, the distribution seems to like fit. So we expect that the transferability is reasonable if the techniques are correct. Yeah, so yeah, so I don't know. I mean, to me, it's like when you are trying to design this kind of benchmark, you are trying to design a hypothesis. So there has to be certain reason that this hypothesis is reasonable, and maybe you figure that out. Yeah, like here,
okay.
Start from part statistics. Yeah.
Okay. Thanks. Maybe I'll let Qixing or audience ask questions and maybe come back if you have time.
Yeah, so I have one question. I think this is a very interesting topic, like really pushing 3D understanding, right? So shape analysis to in the interaction setting using robotic reinforcement learning and advanced machine learning techniques. So I was wondering, do you think this can be applied to scenes, right? So 3D scenes that consist of objects. Of course, the semantics are different, but the 3D scenes also have this kind of compositional structures. The difference probably is that I think for 3D scenes, like the objects tend to be more well defined than the parts in 3D shapes, right? So. But other than that, I think this kind of like the interactions between the objects, the arrangements, objects are also interesting. So what is your perspective on that? Because humans also interact, right, with multiple objects.
Yeah, that's a great question as well. So here's my opinion. I've been working on scene understanding and object understanding for like, I guess like more than 10 years. My understanding is that sometimes people say like scenes are composed by objects and objects are composed by parts. This is like a same level of analogy, right? Global and the part. Somehow I think the key difference is for part structure, for object structure, the coupling of the part relationship is a lot stronger. That's my sense. Whereas in scenes, it's more flexible. Yeah, for example, for the paths to become like to create a seedable area, the 4 legs has to support the cushion area. Yeah, that's kind of a constraint. It's very strong. Whereas in scenes, objects have kind of a loose spatial relationships. So I guess that it's more easier to generate random scenes that still make sense than generating like random objects that makes good sense. So that's a reason that I choose like part decomposition of objects as starting point for this kind of composition generalizability, because I feel that there's like a stronger signal to learn. But I feel that ideally the methodology that we explained here can be transferred to the scene setup, which is, to my sense, is the easier setting. Yeah.
Okay, thanks. So I have another question related to 3D representations, right? So I think how to represent the shapes clearly matter. So previously, I think the 3D representation is designed from the modeling perspective, right? So we want to approximate the surface, right? So like meshes, volumetric surfaces, and then I think in your context, we need a 3D representation that is geometrically, like at least accurate enough, but also it carries the semantics, right? Really for interaction. Do you think this existing from the modeling perspective, right? So do you think the existing representations are sufficient? We just need better machine learning techniques, or do you think like better representations, more semantically related ones, in particular for shapes, could emerge from what you have been doing? Like essentially something that is
my feeling is, first of all, like for the low level representations, like mesh versus volumetric versus implicit functions, I feel that they are like well studied these years. There are a lot of great works and shows the promises. However, if you are like to enable the interactions, right? I feel that being able to model the effect after interaction is very important, right? For example, we manipulate objects in environment, like if we use the microwave, we push the button, the door would open. It's kind of a mobility related aspect. I mean, if you think about that, I feel there has to be a certain abstraction and a detail combination. So some hybrid representation, like we're presenting a cuboid-based representation, I feel that advantage is more, it's more lightweight if you want to process the animation or to predict the consequences, whereas it lacks the details. If you are, maybe you will need to elaborate the cuboids by the local geometries as well, right? So if you want to like understand the deformation or some very detailed geometry. So I think it should have also has its part as a problem, geometry representation for interactions.
Okay, thanks.
Thank you, Shibham and Jishin. I also have 2 questions to ask Hao. The first question, this is on the first or second trick on fixing GNN. This positive, can you hear me? Positive homogeneous. So
I see.
You're removing bias term, which is really shocking to me. I teaching my students in class, bias is important. I'm really doing like this week in my class. So
really?
You want to know when this technique is actually useful. So when I hear bias term, no bias term meaning 0 output to 0. That's the meaning of no bias. So all the problems I saw, counting the connector components or the traveling salesman, so that's bad. 0 goes to 0. The input is 0, no graph, nothing. Output is 0. So that seems to be kind of common property of the problems. I wonder if that's correct, and if any kind of other problems where 0 does not map to 0, this technique that shouldn't be applicable.
Oh yeah. So first of all, Here, I think that I made a kind of vague and quick a point here. So to my understanding, many of the graph theory problems, they actually admit a linear programming way to solve it, right? Basically, you're able to express the problem in terms of linear programming. And usually when the problem has this kind of form, the objective of the linear programming, the coefficients, comes from the graph weights. When it's like that, usually it just gives you like the positive homogeneous problem setup. So I conjecture that although it seems to be like a simple assumption, it covers many problems. Yeah, that's what I know. But yeah, but there are also many problems that are not really like the linear type. I don't have.
Yes, thanks. Actually, this makes sense. When I set lambda to 0, this equality becomes f0 equals 0. So this must be the property. When the input shrinks to 0, your output should be shrinks to 0. So that's the condition.
Yes. Yeah.
Yeah, thank you. Yes, it makes sense. So the second question is on the first project. So my impression is you're essentially using low order property, non-higher order. So first, I say unary property. What a part is? Rotation of a part is those information. Then binary property, relationships, which you classify. But maybe not much higher order. Don't worry about higher order, just local. Unary, binary properties. That's enough to do a good job. So, but kind of higher order is always something cool we want to touch. And wonder, for example, when you do not see a part occluded, looks like you have to give up now. But that's the kind of things a higher order could help. So right now you can basically propagate only 2 because binary is the thing you use. So you can really propagate lots of things to see hidden stuff. So I wonder, as amateur to the field, so how I can maybe use higher order. I just thought that I want the following idea. So say functionality or physical properties or something, that's higher order. So for the thing to stand 4 legs, that's functional property. The functional property is kind of a cross-category generalizable. So if you enforce that as a higher order thing, maybe you can kind of use higher order. So I'm kind of trying to see so far lower order. Is there any idea to use higher order? Still cross-category generalizable.
Okay, yeah, that's a great question. I want to make 2 comments. The first point is low order gives better compositional generalizability. This is also something we observed in a graph neural network setup. So, although in this work, we are saying that the number of layers of graph neural network should be compatible with like the necessary round of message passing. We also have some negative or opposite experiments. It's saying that if your training task and the test task, they are very different and there's no algorithm that is shared between them to solve them. You control the layer of the GNN that might give you a better solution. It's like the low order part might be shared with your training task and test task. High order term is no longer shared. In this term, I use the Occam's scissor. I just sacrifice the high order terms, just align the low order terms. It's helpful. On the other hand, what you mentioned also makes great sense. It's like sometimes we do need high order terms to correct some of the issues. I would think it in this way. Okay, so here, basically, if you leave, I just mentioned like the problem of concept of relationship. Now, if you leave the space of a relationship to be very large, then only considering low order relationships will be helpful. This is a smaller hypothesis class, and it's more generalizable according to like kind of a theoretical understanding. On the other hand, if you will treat high order relationships, and you will strongly constrain the relationship space, I feel it's also possible to figure out the correct high order relation. For example, I guess Qixing has very insightful work online, like the group, like the cycle consistency work, right? I mean, this is obviously a high order problem, but you have a strong expectation of their relationships, like the cycle consistency, which gives you low dimensional structure. So you are emphasizing a very specific high order problem, not making it generalized, generally learnable. Like in graph neural network, basically, if you do that, I mean, you somehow is not able to really control the set of relationships that you want to choose. I mean, the relationships has a too large space, so yeah, the bad relations might be selected. Whereas if you restrict the space, it'll be helpful to deal with the high order relationship. That's my thought, philosophical thought. Yeah.
Thank you again, Hao. So I guess it's time to wrap up. I'd like to thank Hao again for a great talk, and Shubham and Qixing for the questions and discussion. So we have a week of break as a seminar series for the SIGGRAPH submission for many of you, and come back in 2 weeks for this time from Asia. So thanks all again, and also for the attendance. Have a nice day.
Bye. Okay. Thank you. Thank you, Yasu, Shubham, and Qixing for hosting the panel. And thank you for all.
Thanks for the talk.
Yeah. Okay. Thank you.
Thank you.
Bye.